Okay, so a very good morning to all of you, and my name is Navleen Kaur, and the subject that I am going to teach you is theory of computation, and in short, sometimes we call it TOC. The TOC stands for theory of computation, and sometimes we also refer to it as finite automata. Some subjects, some colleges have the subject with the name finite automata, okay, or automaton. It is not automate, it is automaton from automation, okay, finite automaton and theory of computation, right? But for our college, the subject's name is theory of computation. So these are the objectives. So by objective means that what things you are going to learn if you are learning TOC during your semester. So there are some course outcomes. It means by the end of semester, if you finish this subject, so these are the outcomes, these are the benefits that you will get. Okay, so you will be able to use basic concepts of formal languages of finite automata techniques, and you will be able to design your own finite automata for different regular expressions and languages. I believe that in the beginning, it will be next to impossible for you to understand these terms. So I will go over it really quick. And as we will dive deep into each and every topic, so these course objectives will make sense. These course objectives are also available on the top of your syllabus of theory of computation. Before every syllabus subject, there is one objective section where you can see these objectives also. And other than that, you will be able to construct context-free grammar for various languages. You will be able to solve various problems of applying normal form techniques, push-down automata, and Turing machines. And last but not the least, you will be able to solve computational problems regarding their computability and complexity and prove the basic results of the theory of computation. Okay, so these 5 course outcomes are the objectives that you will achieve, and with you I will also achieve if I am teaching you this subject and you are learning it with me by heart. Okay, so the first thing that comes is, as I told you, that TOC and FA, finite automata, they are somewhat same. Okay, so these are the synonyms. So first of all, I will tell you the definition of finite automata, and then we will discuss this definition in a brief also, in a detailed manner also. Okay, so finite automata, short for FA, it is the simplest machine to recognize patterns. Okay, so although it is a theoretical concept, but we are considering that it is a kind of machine. So think that you have a machine. Just picture a machine in front of you, and that machine is capable of recognizing patterns. So here patterns, by patterns I mean strings, right? There are strings of the form A, B, B, A, right? A, B, B. So any machine that recognizes these patterns, right? We call it finite automata. So this is one definition of finite automata. Okay. And if you say that finite automata in itself is made up of 2 terms. Finite means something that is counted, that is limited, something that you can count, that is finite. And what is the opposite of finite? That is infinite, infinity, right? Uncountable. You know that all the states, all the processes that is happening in your computer, they are finite. It's not an infinite machine. Okay, so finite, and second is automata, automatic machine. Your computer is also an automatic machine, you operate on it. Your mobile is also an automatic machine and you operate on it. Okay, now how it operates? It, by it I mean finite automata, it has a set of states. Now states are not like Punjab, Bihar, not that states. State means at any time, at any point of time, what are the values of the variables? That is the state. I'm giving you simple example. So suppose in the beginning, there is a variable A and it has value 2. And then there is a variable B and its value is 3. So if you check the values of A and B at time 0, so the values are A equals to 2 and B equals to 3 at state 1. at time 0. Okay. Later on, if you just change any variable's value, so suppose B's value I change from 3 to 4. Okay. So after some time, after 3 seconds, if you check at time t2, so what is the state of my system? My system has two variables. So you can say that in state 1, the value was A's value 2, B's value 3, but at time t2, the system has entered into state 2 because the variable's value has changed. A is now 2, that is okay, but B's value has been changed to a new value. Okay, so it has a set of states. There are so many states. I'm talking about 2 states only, right? State 1, state 2, but it can have so many states and rules. If your system wants to move from one state to another state, so there are some rules from moving that helps it to move from one state to another. Okay, but it also depends upon the applied input symbol, how it will change the state. There is one input that you provided. For example, the current example says that B's value has a new input. The B's new value is 4. So if a new input is provided, automatically the state will be changed because the values are changed. I will give you an example. You have washing machine at your place. In the beginning, when you are not operating your washing machine, so it will be in the state off. Okay, it will be in the off state. How I can make it to work? How I can change its state from off state to on state? I have to provide some input. What is that input? I have to press the power button on. So when I will give that input, so my machine's state will change from off to on. So obviously there are states that your machine is capable of moving from one state to another state only if you give it the right input. Now, second scenario, suppose it is working, it is in the on state. I want to change the state to off. How I can do it? Again, I have to give one input. What is the input? I have to turn the power button off. Okay. So basically, it is an abstract model of digital computer. So as it is a theory of computation, so it is actually giving you a model, okay, a conceptual view of your computer, that how machine works, okay, any machine, not only your laptop, but any machine around you that is actually computing. Only computer is not computing. Your microwave is also computing device. Your washing machine is also computing device. Your Android phone is also computing device. So this finite automata, this theory of computation is actually giving you a conceptual view of that. Okay, so when I am talking that there are inputs that you provide, so this you can see there are lots of inputs. Okay, so there are inputs like I1, I2, where I stands for input. There is input 1, there is input 2, and so on. There are n inputs. Okay, so for the current scenario where I was telling you that there is a washing machine with you, okay, and you want to change the state from off to on. So what is the input? You turn the power button on. So let's suppose power button on is the input 1. Okay, so with the input 1, your machine will move from one state to the another state. Okay, so suppose Q1 was the state in which it was off. So you provided the input I1, which is power button on. So after you press the power button on, your machine's state now has changed to Q2, because in Q1 it was in off mode, and in Q2 its state means that it is in the on mode. Okay, and why your machine will change the states? Because it will give you some output. So what is the output? If you start your machine, obviously you will get the help in washing your clothes. Got it? So this is the output. Why your machine is changing its states on the basis of the inputs that you provide, because you want certain outputs from it. So this is a diagram that describes finite automata in the best way. So there are lots of inputs and on the basis of those inputs, the states will be changed. The states of automata will change, and why it move from one state to another state? Because you need some output from it. So this is one more example. Okay, so suppose there is a string that you give, and then there is this finite automata. The states will change and it will give you the output. Just wait. So there is some string, right, as an input that you provide to your finite automata, and on the basis of that string's values, it goes from one state to another state. This is just an example. Okay, actually the input is always in the form of some button press. Okay, you press the button, but at the end there are some operations happening inside your machine. You feel like that you have pressed the button and the machine has started, but actually you're pressing the button has initiated some operation inside it. Okay, so here I am representing that your input is of the type string. So if we just want to explain that how your machine is working, so your input, I have considered that it's a string. Okay, and this finite automata is getting that input of the string, and on the basis of that input, it is moving from one state to the another state. Okay, and why it is moving from one state to another state? Because at the end you want an output. So for explaining this entire concept, my input will also be a string and my output will also be a string. This is a conceptual concept, theory concept. So I am considering that input is also a string and the output is also a string. But in real life, the input is button press. The output is you get the new washed clothes. But to explain it theoretically, the theory of computation subject has replaced the input, that is button press, with a string, and the output, that you get a washed clothes, with also a string. Okay, so here when I am saying that output is also a string, okay, so I have changed it a little bit. Now input is a string and it will be passed to the machine, which is finite automaton. Okay, and the output I'm telling you is a string. Why I am interested in that string? I am passing a string, it is again returning me a string. I'm not interested in that. Now what I want, I am saying that if it is getting a string as input, okay, if that is accepted, it means that string is working on the machine. And if that string is rejected, it means that finite automata is not okay with the input. Okay, so it means the string is passed, it will go through different states, and if the final string that you got, okay, it is accepted, it means it is working fine. But if it is rejected, it means it is not working fine. Now the question is, which string will be accepted and which one will be rejected? Let's see it. Okay, this looks quite complicated, but when I will explain it to you, you will say that this is the interesting diagram. Okay, so this is a finite acceptor. So this is a machine, suppose. So this is actually doesn't look like a machine. This is the transition that is happening inside the machine. The machine is moving from one state to another state, to another state, to another state, and then there is a final state. Okay, so this circle here represents the states. This is an example only. There can be any number of states, but the states are always finite, countable. So for this particular example, there are 1, 2, 3, 4, 5, and 6 states. How many states are there? There are 1, 2, 3, 4, 5, and 6 states. Okay. Now there is one initial state when your machine, I am giving you an example, when your machine is in off mode, right? It is there, lying, not started. That is known as the initial state. Okay. When you start it, it will go through so many states. And again, when it will stop, that is known as the final state. Okay. So how you represent your initial state? your initial state is always represented by Q0. First of all, the states are represented by Q, not S. Okay. So Q and 0 is always the initial state. Okay. And then there can be any number of states. And how you can say that this is the final state? A state which has two circles around it. Can you see? There are two circles around Q4. So that says that Q4 is the final state. Okay. So this is the initial state. This is also a 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 state. But this one is the final state. And what is this? Can you see this arrow? Arrow going from Q0 to Q5. Arrow going from one state to another state. One state to another state. One state to another state. Q1 to Q2. Q2 to Q5. So there are always transitions between the states. So transition is always between the states. It means one state is changing into another state. Now I told you that the system will change state only on the basis of some input it gets. So here this A, this B, this A, this B, this A, this B, so many A's and B's, they are the inputs. Okay. And Q0 with an arrow like this coming from nowhere, it specifies that this is the starting state. From here you have to start it. Sorry. Okay. So now I am giving this transition diagram, an input string. Okay. What is the name of my input string? It is, consider this capital A as small. It is A, B, B, A. Okay. I am giving it input A, B, B, A. Okay. So can you see when Q0, this Q0 gets input, this one, A. If it gets input A, where it moves? So this is the A, it moves to Q1. It changes the state Q1. So that is explained here. For you people, it is very well explained that in the beginning, the string is A, B, B, and A. And we are passing this string to this transition diagram and see that if this string is accepted by this transition diagram, by this machine, or if it is rejected by it. Okay. So here with the help of this, I have explained it step by step and it will be very easy for you. And this transition diagram, sometimes it is available, sometimes you have to create it. For this example, you will get an already created diagram. Okay. And there are scenarios when you need to create it also. Okay. And I will help you how to create it. So for now, don't get bothered that from where you got it. This is for this particular example and it will be available like this. Okay. So I was telling you, bache, that Q0 if Q0 get input A, it will move to Q1. But if Q0 get the input B, it will not move to Q1. It will move to Q5. Okay. Similarly, if you got A and you move to Q1, after that, if Q1 get A, you will move to Q5. But if you get B to Q1, you will move to Q2. Okay. If Q2 will get A, you will move to Q5. But if it will get B, you will move to Q3. So this is how it is explained. Q3 will get B, you will move to Q5. Now Q5, if get A or B, in any case, if the input to Q5 is A or B, it will again come back to Q5. Okay. This is the transition diagram that is already available. Q3 will get the input A, so it will reach the final state. Okay. From the final state, if there is any input given, A or B, it will again reach to Q5. Okay. So it means it's not like that in the final state, you can't give it any input. You can again start it. Okay. So this is available. Now we will check that to this finite automata, if we provide the input A, B, B, A, how will it react? Okay. So the same diagram is copied here. And the string is, this is the input string A, B, B, A. Can you see this is the same string I copied here? And now I will check that for this input string, for this set of states and transitions, whether this input string will be accepted or not. So we will go over the string one by one. So the first character of your input string is A, and you are at starting state. In the beginning, your system is at the starting state Q0. So that's why Q0 is being highlighted in red. It means your state of the system is Q0, starting state. Okay. Now A will be processed. Can you see? A will be processed. So if A will be processed, it means I'm not going in the direction of B. No, I am not interested in it because the first input to my starting state Q0 is A. And if it is A, automatically my system's state will now become Q1. After reaching Q1, if I again check what is the next input I will get, that is B. Okay, so for B as the input, automatically my system will reach to Q2. Again, I will check the next input is again B. So for the next B, I will say that my state of the system is now Q3. Again, there is still one more character of my string pending, that is A. So if I will input A, so the state from Q3 will automatically move to Q4. Okay, so for all A, B, B, A, starting from here, it has reached the final state. So what is the criteria that this string is accepted or not? So listen very carefully. If for any string you are able to start and reach at the final state, it means if any string help you to reach to the final output, final state, it means that string will be accepted. But if a string is not taking you to the final state, it means that string will be rejected. Okay, so as this A, B, B, A, B, B, A is taking you to the final state, it means this is accepted. Okay, let's do one example of rejection of a string. Okay, so same transition diagram I am in the starting state Q0. Okay, and the first string word, first letter that I got is A. Okay, so for this A, my machine will move from Q0 to Q1. Okay, can you see here? After that, second string will be processed and it will take B, it will give B to Q1 and the state will change to Q2. Very good. But after that, I have still one more last letter of my string still pending. If I will give this as input to Q2, the state will move not to Q3 but to Q5. Okay, and after that I got nothing. This was the last element of my string. It means this is the last state I am getting. So can you see this string ABA is not taking you to the final output. Instead, it is taking you to a normal state. So that's why you can say that this string is rejected by your finite automation machine. So I have one more example, and this time the diagram, the transition diagram, the finite automata diagram has changed. Okay, and this is the string that we have to pass to this transition diagram, and we have to check that whether this will be accepted by this transition diagram or not. And I told you that what is the criteria, that if a string is accepted, a string will be accepted only if it will take you to the final state. Okay, but if it is not taking you to the final state, you are still on a normal state in between, so you can say that that string is rejected. So let's do this new diagram with this new example of string. So your machine is in the starting state Q naught. Okay. Now see, if I pass it A, okay, so what will happen? This is the first element of your string, so you have to start from A. If you pass it A, this Q naught will get A. Can you see it is again coming back to Q naught? Like this. So first A is processed, Q naught got the input A, but the state remains the same Q naught. Now we are on the second element of your string, that is A. Again A. Now if that A is again passed to Q naught, what will happen? It will again move to the same state Q naught. Same thing happened. Now after that, you have again come back to Q naught. Now Q naught gets B. So if Q naught gets B, this one, it reached to the state. A state with the double circles. I told you that if a state has double circles around it, it means it is a final state. Oh wow. This AAB has taken your finite automata into the final state. So what do you think, that whether this AAB is being accepted or rejected by your finite automata? Is it accepted or is it rejected? So what is the output? So output you will write accepted. It is accepted. Okay, so with the same diagram, there is one more example of the string, but this time it will be rejected. Okay, why it will be rejected? We will see it. Okay, so it is in the starting state, that is Q naught. Okay, so your Q naught got the first input from the string, which is the first element, that is B. Q naught got B, and Q naught, after getting B as input, will not go here. It will go here because here the B is. So Q naught will reach from Q naught to Q1. Like this. Okay. After B, the next input, that your new state, Q1 will get, it is A. Okay. So now Q1 is getting A. So Q1, whether it gets A or it gets B, it moves to Q. Okay, but now it is getting A, so automatically it is moving to Q2. So sometimes there is comma, there are multiple inputs given between two states. What these multiple inputs mean? It means that if Q1 will get A, even then it will reach to Q2. But if it will get B, even then it will reach to Q2. It means it is not worried about the input. If the input is A or B, in both the cases, the state, new state will be Q2 from Q1. Okay, so as we got A, and here A is mentioned, Q1 got A and you reach to Q. Okay, so still we have one more one more letter to process, that is B. So if your Q2 gets B, so here again it is mentioned that if Q2 gets either A or B, it will again come back to Q. So for the current scenario, it is getting B. So it means it will again come back to Q2. And your string is now ending. There is nothing after that. It means this is the last thing. So after processing the whole string, you are in Q2. Okay. So which is not the final state. So what do you think? Is it accepted or rejected? Now let's discuss the different types of finite automata. Okay, so it can be classified into two types. There are two types of finite automata. Okay, first one is known as deterministic finite automata. Okay, deterministic finite automata, that is known as DFA. And second one is non-deterministic finite automata. Sometimes it is known as NDFA, or sometimes it is normally known as NFA. Okay, so one is deterministic finite automata and other one is non-deterministic finite. So first of all, I'm going to explain deterministic finite automata. Okay, so finite automata, you already know that there is a transition diagram, there is some input string. It will go through the transition diagram and you will see whether it will be accepted or rejected. Now the category is whether it is deterministic finite automata or it is a non-deterministic. Okay, so deterministic means something that you can determine, right? something that you can check, you can predict. Okay, I can determine this thing, that he is very shy. I can determine this thing, that he is good or she is beautiful. So something that you can confirm, you can determine. Okay, that is known as deterministic. I'm explaining this word deterministic. On the other side, non-deterministic means the opposite of it, something that you can't determine. Okay, so now let's study this deterministic word with respect to finite automata, what we call deterministic finite automata. Okay, in deterministic finite automata, for each input symbol means every letter of your input string. For each letter of your input string, one can determine the state to which the machine will move. So what we are going to determine? We are going to determine the states. If you have input symbols and you are able to determine that on the basis of this input symbol, what will be the next state? It means it is the deterministic finite automata. But if you are not able to determine what will be the next state, it means that will be the non-deterministic finite automata. Okay, so for all the examples that we were studying previously, for every state, if there is an input, you know that you are able to determine what is the next state. If it is B, you are able to determine next state is Q1. If to Q0, the input is A, you are able to determine the next state is again Q0. Okay, so here deterministic means for every input to a state, if you are able to check that what will be the next state, what is going to be the next state, you are able to determine it, you are able to check it, then it is known as deterministic finite automata. Okay, it is called deterministic automata. And as it has a finite number of states, your machine always has finite number of states. This machine has 3 states, which is finite. The previous one that we were studying, it has 6 states. That is also finite. That's why it is known as finite automata. Okay. As it has a finite number of states, the machine is called deterministic finite machine also, or deterministic finite automata. Machine and automata are same. Machine is automatic already. Okay. So after that, there is one good definition of deterministic finite automata here. Okay. And some people may think, oh my God, this is mathematical concept. It looks like, because there are so many symbols, every symbol has its meaning, there are transitions. But when I will explain it to you, you will see, okay, everything makes sense. So let's go through it. Okay. So for this M, for this deterministic finite acceptor, this M machine, okay, the machine which is deterministic finite acceptor or automata, it is represented with M, and it can be represented with how many symbols total? 1, 2, 3, 4, 5. There are how many symbols? 1, 2, 3, 4, and 5. Okay, so every deterministic finite automata, by deterministic finite automata means this thing. Okay, here, this transition through which it is going from starting to the other stage. Okay, so for every DFA is represented with M, and it has 5 symbols. These 5 symbols, it is represented by 5 symbols. It is not more than that. So let's see each one. Q, the first one is Q. What is Q? Finite set of states. Countable set of states. Q represents countable set of states. Okay, so for this example, what will be Q? Q will be countable set of states. How many set of states it has total? 1, 2, 3. Okay, so Q represents how many states it has. Q is set of states. Okay, then this, I think this is explained further also. So you got that Q is finite set of states. After that, there is this summation symbol. It is known as input alphabet. Okay, so you know that all your inputs were made of only 2 symbols, A, B, right? All the input strings, they are made up of only 2 symbols, A, B, for these examples. Okay, so input alphabet means all the symbols that you are using for input. So here, this example says that sigma is A, B. This was the example that I explained to you first. Okay, so what is capital Q for this? The capital Q is Q naught, the set of states, that is Q naught, Q1, Q2, Q3, Q4 and Q5. What is the input symbol? Input symbol means the symbol that you are using, the set of the symbols that you are using, that is A, comma, B. After that, what's next? Next is Q naught. Let's do it later. Next is Q naught. Q naught, what's Q naught? It is initial state and it is a member of your total set. Okay, Q naught, it is the initial state. For this example, this is your Q naught. Initial state is known as Q naught. And obviously, it is a set of Q. It is a part of, it is a member of Q. Q naught is a member of Q, the whole set. So Q naught is your initial state and it is a member of the finite set of state. And then there is capital F, that is the final state. Here it is mentioned set of final states. So students, sometimes there is not only a single final state, there are multiple final states. That's why it is mentioned set of final states. But the initial state, that is only one, Q naught. But F can be a set of final states. For this particular example, what is F? F is, there is only one final state, that is Q4. Okay, but if for any other example there are multiple states, so you will write Q4 comma the other final states. Okay, and one thing that is left, that is sigma. Okay, now what is this sigma represents? It is the transition function. You have worked on how many states you have worked on how many inputs you have worked on what will be the starting state, you have worked on what will be the final state. But why you need all these states, this input? You have to move from one state to the another state. Now this sigma is actually the transition function that will help you to move from one state to the another state. So your transition function is represented by the states, all the states multiplied by what inputs you give it. Okay, every state, there are so many states, so you are writing Q. Okay, and multiply by what input you give it from the input alphabet, and it will take you to a new state because states are represented with this Q. So your sigma is states multiplied by input alphabet and what final state you will get as the output. So here it must be explained, this one. Okay, so if state is Q naught, this Q's value is Q naught and input you are giving it A, so the final Q will be Q1. If your state is Q2 and the input alphabet you are giving it A, so the final state will be Q5. Okay, so I hope that I have made it enough clear to you with the help of an example. Okay, so they have explained the transition function and other things are already clear. So let's go through transition function in more detail. So transition function is any state to it to give any input symbol and it will give you a new output state. Okay, so here it is explained with example that sigma, okay, to Q naught state. It means here Q is your Q naught. Okay, you are taking Q naught. And what is the input symbol you are giving to it? You are giving it A. So Q naught is getting A. And what output state you are getting? You are getting Q1, right? So if your input Q naught, sorry, your starting state Q naught is getting input A, so it is being passed to the final state, which is Q1. One more example. If Q naught is getting B, you will reach to output state Q5. So Q naught and input symbol B, it will take you to some random example. Nothing to do with the transition, some random examples for transition function. Okay, one more example. If the state Q2, it means you directly move to Q and it gets B, okay, B, you will reach to Q. Okay, so if you want to represent this in the form of a transition table, so this is how you represent it. Okay, so this is your transition function. This is transition table. Okay, let me explain it to you. It is also very easy. Okay, so this is the last thing we are going to cover today. And here this is the sigma, the transition symbol, and here on the top there are two inputs. Okay, So when you create, if you are given with the transition diagram in the paper and you are asked to generate a transition table, so how to do it? Okay. So at the top, you will first write transition symbol, then you will write the input variables. There are two input variables. That's it. Sigma is only A and B. You start from the first state, the initial state, Q naught. Okay. Always write first Q naught. Okay. So if Q naught gets A, this is how you do it. If Q naught gets A, where you reach? If your Q naught gets A, you will reach to Q1. That's why here Q1 is written. Okay. But if your Q naught gets B, where you reach? If your Q naught gets B, you will reach to Q5. Now let's talk about Q naught is done. Q naught can get maximum two inputs, A or B. If it gets A, it will reach to Q1. If it gets B, it will reach to Q5. So I am done with Q naught. Now let's talk about Q1. Okay. If Q1 gets A, it will move to Q5. But if Q1 gets B, it will move to Q2. Very simple. Now Q1 is also getting maximum two inputs, so it is done. Okay, because we have only two input elements in the input symbol. Next is Q2. If Q2 gets A, you will move to, there is some issue I think here. Q2 gets A. Q2 gets B. Here there is a mistake that we have to correct. If Q2 gets A, you have to write Q5 here. Okay, let me just check. Okay, so if Q2 is getting A, so it is moving to Q5, but if Q2 is getting B, Q2 getting B, it moves to Q3. Okay, so Q2 is done. Next is Q3. Now Q3, if gets A, Q3 gets A. Can you see here? Q3 gets A, it moves to Q4. So Q3 for A moves to Q4. But Q3 for B moves to Q5. That's mentioned here. Q3 for B moves to Q5. Okay. Q4 A for A. Q4 for A moves to Q5. Q4 for A moves to Q5. But Q4 for B also moves to Q5. So Q4 for B also moves to Q5. Okay, last one, Q5. Q5 for A also moves to Q5. Q5 for B also moves to Q5. So everything rest is correct. There was only a minor issue with this one. And this is the transition function, transition table that you can create.